lecture for properties of functions. This is lecture 8, part 2. This is for college algebra, and my name is Jorge. So for lecture 8, there are actually 3 videos, and one of them, the first one, we talked about graph of functions, and for the second and third video, we're going to be talking about properties of functions. So the objectives for part 2 and part 3 are the following. We're going to go ahead and determine even and odd functions from a graph. We're going to identify even and odd functions from the equation. We're going to use a graph to determine where a function is increasing, decreasing, or constant. We're going to use a graph to locate maxima or local minima. We're going to use a graph to locate the absolute maximum and absolute minimum, and then we're going to find the average rate of change of a function. So the first thing is an even function. So a function f is even if for every number x in its domain, the number negative x is also in the domain. And f of negative x is equal to f of x. So for an even function, for every point xy on the graph, the point negative xy is also on the graph. Now a function is odd if for every number x in its domain, the number negative x is also in the domain, and f of negative x is equal to negative f of x. So for an odd function, for every point xy on the graph, the point negative x, negative y is also on the graph. So the theorem states that a function is even if and only if its graph is symmetric with respect to the y-axis. A function is odd if and only if its graph is symmetric with respect to the origin. So here we have the graph of 3 functions. So we're going to determine whether they're even, odd, or neither. So the first one is an even function because, as you can see, it is in fact symmetric with respect to the y-axis. So the y-axis acts as a mirror. The second function is neither because it's not symmetric with respect to the y-axis or the origin. And the last one, it's actually an odd function because it is in fact symmetric with respect to the origin. So we can actually determine this algebraically, and we're going to do that with these 3 examples. So if you remember, in order for it to be even, f of negative x has to equal f of x, or for it to be odd, f of negative x has to be equal to negative f of x. So what we do is we replace x with negative x. So f of x now becomes f of negative x, and if we end up with the original function, then it's even. If we end up with negative 1 times the original function, then it's odd, and if we end up with something completely different, then it's neither. So here we replace x with negative x. We evaluate, and here we can see that if we remove a negative 1, we end up with the original function but a negative 1 outside. So therefore, f of negative x is equal to negative f of x. So therefore, this is an odd function, and it is symmetric with respect to the origin. The second one is g of x. So we're going to go ahead and replace it with x with negative x. And by evaluating it, we end up with the original function. So g of negative x is actually equal to g of x. So therefore, this is an even function, and it is symmetric with respect to the y-axis. Now the last one, we find out that we actually end up with a different function altogether. So therefore, this is neither even nor odd, and it is not symmetric with respect to the y-axis or the origin. So now we're going to determine whether a function is increasing, decreasing, or constant. And we're going to look at the graph to determine this. So where is the function increasing? So here we can see that between when x is negative 4 and x is 0, the function is actually increasing. Oh, excuse me. So, and it's increasing because f of negative 3 is actually greater than f of negative 4. F of negative 2 is actually greater than f of negative 3, and so on up to when x equals 0. So when x equals 0, it is greater than all of the values that came before it. Now where's the function decreasing? So it's decreasing between when x is equal to negative 6 and x is equal to negative 4. And the way that we know it's decreasing is because f of negative 5 is actually less than f of negative 6, and then f of negative 4 is less than f of negative 5. And it's also decreasing between 3 and 6, and again, the same thing applies, right? So 3 is less than 6, and f of 6 is actually less than f of 3, so therefore is decreasing in that interval. And that's what we call interval. So when x is negative 6, between negative 6 and negative 4, that's an interval. Between 3 and 6, that's an interval. So where's the function constant? So we can see that the function is constant between 0 and 3. And that means that f of 0 is actually equal to f of 3, or f of 1 is equal to f of 0, f of 2 is equal to f of 1, and so on and so on. So therefore the function is constant. So here's a formal definition. A function f is increasing on an open interval I if for any choice of x1 and x2 in the interval, when x1 is less than x2, we have that f of x1 is less than f of x2. Function f is decreasing on an open interval I if for any choice of x1 and x2 in that interval, x1 is less than x2, and we have that f of x1 is greater than f of x2. And a function is constant on the interval I if for all of the choices in x within that interval, the values of f of x are equal to each other. So here we have some more examples. So the first one, as you can see, that x1 is less than x2, and f of x1 is less than f of x2. So therefore, in the interval between this open circle and this open circle, the function is actually increasing, or between the interval of x1 and x2, the function is actually increasing. Here, for the next example, x1 is less than x2, and f of x1 is actually greater than f of x2, so therefore it's decreasing. And then here is a constant function, x1 is less than x2, and f of x1 is actually equal to f of x2. Local maxima. So here we can see that between the open circle and when x equals c, the function is increasing. Now, between c and the open circle here on the right, the function is decreasing. So that means that f of c is what we call a local maxima. So increasing, decreasing, there's a high point, if you will. So here we have local minima. So the function is decreasing here in this interval. It is increasing in this interval here between the closed circle and the open circle. So therefore, f of c is what we call a local minimum. So here's some definitions. A function f has a local maximum at c if there's an open interval I containing c such so that for all x not equal to c in the interval, f of x is less than or equal to f of c. So therefore we call f of c a local maximum of f. A function f has a local minimum at c if there's an open interval I containing c so that for all x is not equal to c in the interval, f of x is greater than or equal to f of c, and this is what we call a local minimum of f. So here we have another example, right? So we're going to go ahead and find local maxima and local minima from the graph. We're going to determine whether the function is increasing, decreasing, or constant. So at what numbers, if any, does f have a local maximum? So here we can see that the local maximum occurs when x equals 1. And so what's the value of that local maximum? The value for that local maxima is 2. So at what numbers, if any, does f have a local minimum? So here we can see that minimums occur when x equals -1 and x equals 3. And so what are the values for this local minima? Is 1 and 0. So list the intervals on which f is increasing. So we're looking for which intervals is the values of the functions actually increasing as we keep moving to the right. So the function is actually increasing between -1 and 1. So here we can see that from -1 to here the function is actually increasing, and it's also increasing from 3 to infinity. So list the intervals in which f is decreasing. So we can see that it's decreasing from -infinity to -1, and also decreasing from 1 to 3. So it's decreasing here and it's decreasing in this interval. And that's the end of part 2, lecture 8. Thank you.